Welcome to the course Content-Based Image and Video Retrieval, Module 2 Video. Myself, Meherban MS, Assistant Professor, Department of Computer Science, Rajagiri School of Engineering and Technology. The next is a very important feature which is called texture. So let's see what are the different methods for texture extraction method and what is meant by texture-based features. So texture is a powerful discriminating feature represent almost everywhere in nature. Texture similarity, however, is more complex than the color similarity. And the two images can be considered to have a similar texture when they show similar spatial arrangement of color but not necessarily the same color. So there are several possible approaches to represent and extract the texture properties of an image, and there are mainly three main categories of texture model that I will explain later. Let's see some of the examples of textures. Here you can see the different types of textures. First one, statistical model. So statistical approaches to describe the texture properties usually fall within one of this category. The use of statistical moments of the gray level histogram of an image or region to describe its texture properties. And the second moment is of particular because it measures the gray level contrast and can therefore is used to calculate the descriptors of relative smoothness. And histogram information can also be used to provide the additional texture measures such as uniformity and average entropy. So similarly to what was said for color histogram as color descriptors, the main limitation of using histogram based texture descriptor is the lack of positional information, and the use of descriptors like energy, entropy, contrast, homogeneity can be derived from the gray level co-occurrence matrix. This is an example of GLCM. Here you can see input image, and let's see how many number of pixels, the maximum number of pixels. So here it is 8. So you can represent a gray level co-occurrence matrix consists of 8 rows and 8 columns. And first of all, we need to check the 1 1 1 there is any adjacent pixels are there. So here you can see there are only one adjacent pixel is available for 1 1. So the count is 1. And let's check for any 1 2 is available. Yes, you have 2 occurrences are there, so the count is 2. And check for if there is any 1 3 is there. So there is no 1 3, so you can put it as 0. So this is a gray level co-occurrence matrix, and from this matrix you can extract the different texture features. What are the different features we can extract? I will explain in the coming slide. First feature is the angular second moment. So angular second moment is also called uniformity or energy, and it can be computed as the probability of the pixel square value. So angular second moment is high when the image has very good homogeneity or when the pixels are very similar. So this is an equation. Sigma is equal to 0 to ng minus 1, that is a maximum number of pixel minus 1. Sigma j is equal to 0 to ng minus 1, the probability, that is p square of the pixel ij, and where ij are the spatial coordinate of the function and ng is the gray tone, that is 0 to 255. And the next feature is called entropy. So entropy shows the amount of information of the image that is needed for image compression, and entropy measures the loss of information. So it can be computed as minus Pij into log Pij. And third one is called correlation. So correlation measures for linear independency of the gray level of neighboring pixel, and the correlation can be computed as Ij into P of I comma j minus mu x mu y divided by sigma x sigma y, where mu x and mu y is representing the mean value and the variance which can be represented as sigma x and sigma y. So let's see one example how you can extract the gray level co-occurrence matrix and how you can extract the different texture features. So here you can see my query image, and after that I have converted into a grayscale image. Then I will construct a gray level co-occurrence matrix from this gray level image. The gray level co-occurrence matrix that I developed from the previous image. And in this table, I have extracted the different features from that image, that is entropy, correlation, and for the different block size, that is 64 into 64 for 128 into 128 and 256 into 256. And the next texture feature, which can be called spectral model, and it is based on the spectral density function in the frequency domain. So in normal image processing, we are generally consider for the pixel domain and the frequency domain. So the advantage of frequency domain will get a more detailed information rather than the pixel domain. So why we are using a frequency domain? In order to get more details about the information, or in order to get more details of particular image, we can go for frequency domain. So here we have using a transform. So transform, it's act like a simple prism. Suppose I hope all of you know the concept of dispersion in physics. A white light is passing on a prism, it is splitting into 7 constituent color, which is called dispersion. So similarly, if an image is passing on a transform, we'll get a more details. So that is we are using transform. So there are different transform are already developed. So first one called wavelet transform, and it is considered to indicate the correlation of brightness pattern in an image. And there are different type of textures. One is called coarse textures, will have the spectral energy concentrated at low spatial frequency, and there will be a fine textures will have the larger concentrations at a high spatial frequency. Here you can see the examples of spectrum. That is, we can split the image into 4 band, that is low band, low band, low high band, and high band. And again the low band we can split it low, low high. Similarly, depending upon the size, we can split it the image, and based on that you can determine the frequency component of an image. Next method called structural models. So in this model, we describing the texture in terms of the primitive texels in some regular or repeated relationship, and this approach is appealing for artificial and regular pattern. So moreover, it is fundamentally a problem of scale, and that is why it is though difficult to find the texture descriptor if the data set is, or if the database is unconstrained. So far we have discussed the different methods of color and texture features. So in this slide I'm going to explain what are the different methods of shape feature extraction. So color and texture are both global attributes of an image, and shape goes one step further and typically requires some kind of region identification process to precede the shape similarity measure process. So an image must be segmented into meaningful objects and background before applying the most shape descriptors. In many cases, this has to be done manually, but in restricted domains, the automatic segmentation is possible. So segmentation of difficult scenes is an open problem in computer vision. So let's see what are the different shape features for a particular geometry, that is for ellipse. So here you can see the features like extreme point, feature point, shape centroid, and the axis of least inertia are the features can be extracted from a ellipse. This is another example for shape feature extraction by using an edge detectors. There are many edge detectors are available like a Canis, Sobel, Robert, and Privet. So shape representation technique can be classified in three broad categories. First one called feature vector approach, and second one is a relational approach. So in this case, a shape is represented as a numerical feature vector whose elements are the prominent attribute of the shape. And third one is a relational approach. So methods in this category break down a shape into a set of salient component parts. So these are individually described through a suitable features, and the overall description includes both the descriptors of the individual parts and the relationship between them. In this slide, you can see the segmentation part, that is called semantic segmentation, and after that we have identified the different object based on that semantic segmentation. And next method is called shape through transformation. The shapes can also be distinguished by measuring the effort needed to transform one shape into another. And it is very hard to perform accurate and meaningful shape-based similarity comparison without resorting to segmentation. And segmentation in an unconstrained context is difficult, sometimes it is meaningless. So the contribution of shape in general purpose of Cbivr system is very difficult. So most of the case we are consider only the texture and color information. And if you want to develop a more accurate Cbivr system, then you can incorporate the shape feature also. This is a basic example for the instant segmentation and the difference between that object detection. So here we have three different objects. You can see the dog and the cat, and we have detected the object and we can segment the object also. And next is some of the specialized features. So most of the efforts in current Cbivr system development has been concentrating on color, texture and shape, and we can incorporate some specialized features. So if the users might be interested in objects such as people or dogs, even more abstract concepts such as poverty or happiness, some VIR systems have experimented with the specialized features, and they're used to detect specific objects or concepts. And some of the examples are face finding, flesh finding, and retrieval by objects and their spatial relationships. And next is, what are the different type of similarity measurement. So after the color, shape or texture information is extracted from an image, it is normally encoded into a feature vector. And given two feature vectors x1 and x2, a distance function computes the difference between them. And it is hoped that this difference will accurately measure the dissimilarity between the images from which the features were extracted. And greater the distance, less the similarity. And most commonly used distance functions are called Euclidean distance and city block distance, and Euclidean distance which is called L2 norm, and the city block distance which is called L1 norm, and which is also known as Manhattan distance. Let's see the different distance measure, that is called Euclidean distance. It can be computed as square root of x1 of I minus x2 of I the whole square. The next one is just Manhattan distance, which can be represented as x1 of I minus x2 of I. And the distance functions or metrics observe the following properties, that is the distance of p comma q, which is always greater than or equal to 0, and the distance of p comma p, which is equal to 0, and which is also satisfying the commutative property, and which is also called symmetric, p of q of distance which is equal to distance of q comma p. And the next one, distance of p comma z, which is less than or equal to distance of pq plus distance of q comma z. And the last distance measure, which is called histogram intersection measure, which can be represented as sigma of I is equal to 1 to n min of x1 of I comma x2 of I divided by sigma I is equal to 1 to n x1 of I. The next is how we can reduce the dimensionality and how we can perform the high dimensional indexing. One of the main challenges is the high dimensionality of that feature vector. So solution to the high dimensional indexing problem include reducing the dimension of the feature vector and use of efficient multi-dimensional indexing technique. So when we're dealing with very large image database, it might become impractical to do the linear search, the whole database for image and to satisfy the given query. Instead, the images must be organized and indexed so that only a fraction of them are considered during a query. So index sectors ideally filter out all irrelevant message while retaining the relevant images and which are then ranked in order to get the similarity according to the query. So most of the text-based BAR system is conveying on conventional indexing technique for textual information such as hash table and signature file. So among the proposed solution to the problem, the KD tree and their invariant, R tree and their variant, SS tree and invariant are commonly used. Let's see what is meant by clustering. So clustering is the process of grouping the data into classes or clusters so that the object within a cluster have high similarity in comparison to one another but are very dissimilar to objects in another cluster. So clustering is a widely used approach for unsupervised learning in pattern recognition, data mining and related area. The motivation for using clustering in Cbivr systems seems from two different reasons. First one is from a visual perception point of view, it is expected that the clustering the feature vectors obtained as the result of a particular feature extraction module would group together images that look according to that feature. From the computational point of view, dealing with clusters instead of individual images while performing the required calculation in each iteration should reduce the time spent on those calculations by at least one order of this magnitude. One of the biggest challenges in using clustering to group visually similar images is to find a feature vector clustering algorithm combination that provides visually meaningful results. This is basically a clustering. So here you can see the similar object is grouped into three clusters. You can see the red, blue and green clusters. The next one is what I mean by semantic gap. So human perception of visual content is strongly associated with high-level semantic information. But the problem is in the current computer vision techniques, it allows only for a low-level features. So Cbivr system is working on low-level features. Suppose one query is like find all images that have a blue sky above a green grass. Find all images that are rotated version of this particular image. So in order to find the answers for this particular query, the traditional Cbivr system is very difficult because the Cbivr system which is deals with the low level features. The problem is the user is looking for high-level semantic features of a desired image, such as a beautiful rose garden or a batter hitting a baseball or an expensive sports car. So there is no easy or a direct mapping between the low-level features and the high-level concept. So the distance between these two worlds are normally known as semantic gap. There are mainly two ways of minimizing the semantic gap. The first consists of adding as much metadata as possible to the image, which was already discussed and shown to be impractical. That is, we need to add the text description for each images in the data set. So that is a quite tedious task. The second is use of user relevance feedback combined with the learning algorithm to make the system understand and learn the semantic context of a query operation. So let's see what is relevance feedback in the coming slide. The expression "the relevance feedback" has been used to describe the process by which a system gathers information from its users about the relevance of features, images, image region, or a partial retrieval result. Such feedback might be provided in many different ways, and each system might use it in a particular manner to improve its performance. The expected effect of relevance feedback is to move the query in the direction of relevant images and away from the non-relevant ones. So in this example, you can see the images are retrieved and our query image is a tiger one. And here the similar images we have adjust the weight, we have assigned the weight, and based on that we can retrieve the images which are more relevant to the query image, and some of the images in the first row, the fourth and fifth one are irrelevant one. We can remove that based on that adjusting that feature weight. And in this figure you can see most of the images which are relevant one, and most of the images are relevant to the query image. So this is a basically a relevance feedback technique, and many methods we can apply for relevance feedback method. In Cbivr systems that support relevance feedback, a search typically consists of a query followed by a repeated user feedback, and the user is comments on the item that were retrieved. The use of relevance feedback makes the user interaction with the system simpler and more natural. There are many ways of using the information provided by the user interactions and refining the subsequent retrieval results of a Cbivr. One approach concentrates on the query phase and attempts to use the information provided by relevance feedback to refine the queries. Another option is to use the relevance feedback information to modify the feature weight. In the previous example that we done, use relevance feedback to construct new features, and the fourth possibility is to use the relevance feedback information to update the probability of each image in the database being the target image. Let's see the benchmarking Cbivr solutions. The benchmarking visual information retrieval solution is an open problem, and here is a summary of the latest recommendation issued by the technical committee from the International Association for Pattern Recognition regarding the benchmarking for visual information retrieval. So the first benchmarking solution is an extensible suite of benchmarks that consists of a number of component sets that cater for different applications requirements should be developed. The second one, the resultant image collection must be freely available to research to experiment on and free from any conditions or restrictions. And third one, to minimize the dependence on hardware and other extraneous factors, the entire image collection in question should be stored in main memory during the evaluation. And the fourth one, the initial number of images in the object-based photograph category should be 1000, and which may be scaled up at later stage. The next one is the photographic image should contain multiple objects, and the image should be in JPEG format, and the set of 20 evaluation queries which cover a representative cross-section of the contents. The queries should be based on the visual content of the image. For each query, there should be non-answers that do not exceed 15 images. And the last one, images returned for possible browsing should not be greater than 15 at any time. And the last two benchmarking solutions are the measures to be used for evaluating the system performance should be recall, precision, the average number of stages for retrieving the relevant image. And the next one, speed is not a critical concern, but while we clearly but we can't ignore the speed of the retrieval completely. So let's see some of the important questions that we can expect for the exams. Explain the different methods of feature extraction, explain the different color models, illustrate the different texture feature extraction methods, semantic gap, how to overcome this gap, the different solutions for benchmarking Cbivr, and compare and contrast the color concurrence and color coherence vector, explain the different similarity distance measure, and also explain the different properties and the different shade feature extraction methods and the different types of texture feature extraction methods. So thank you all for watching this video.